There you go.
Hi, this is Bob Westervelt. Today we have Kirasone from UMass Boston will be talking with us about quantum computing. Kira got his PhD from MIT on a sort of a similar topic, thinking about how to program quantum computers and make them work better, and then went to Los Alamos, where he did some related work before coming back to UMass Boston. A problem that people have now is that if we had error-corrected qubits and about 1 million of them, we would be rolling, because then we could decrypt encrypted messages and all of that. But we're sort of in the first steps, where we have hundreds of physical qubits that have a lot of noise. And so people are looking short-term at problems about how, instead of decrypting things, how can you solve more modest but still very difficult problems by sufficiently clever, and we'll be telling us about that today.
Yeah. So thank you, Paul, for introduction. First of all, thank you very much for your invitation to the QMD seminar. My name is Kirasone. I'm right now assistant professor at the University of Massachusetts, Boston. And today I'm going to talk about the near-term quantum algorithms and its application. So the recent development in the quantum computing, so we have lots of progress right now in the recent research in the quantum computing area. For example, in 2018, the United States has signed this National Quantum Initiative Act. This is actually a 10-year plan for the accelerating the quantum research and development for the economy and national security of the United States. And then when I graduated from the MIT, I graduated in 2019, and so in this year, actually, IBM actually announced their first commercial gate-based quantum computer called IBM Q system, and this is composed by the 20 superconducting qubits, and actually the customer can perform quantum computing over the internet by using their own the IBM's quantum computer, And then 2019, 2020, there's a big progress in the quantum computing area. Actually, this was achieved by the Google and USDC in China. So they sampled the random quantum circuits, and the Google Sycamore, actually, they claimed that they achieved so-called quantum supremacy. So they sort of sampled the random unitary circuits, and then they did this task within the 200 seconds, while the supercomputer was supposed to take 10,000 years to complete this task. But then IBM argued back, said it's not 10,000 years, but it's 2.5. It's not 200 seconds, sorry, 200 seconds, but 2.5 days. And then so they argued this in the back and forth. And then 2020, Chinese scientists claimed that they used their quantum computer made by the photonic qubits. Actually, they completed a task within the 3 minutes, while the supercomputer would need 2 billion years to solve this similar task. So as you can see, that right now the quantum computing is a very hot topic right now. And actually, there has been today the many universities and companies and laboratories are coming together and compete with each other to try to really build up this device to achieve to make this device work. So many countries have invested a lot of money to the research. So the quantum computing right now actually becoming is becoming a growing reality from I would say scientific curiosity. Well, so let's briefly look at how the quantum computer works. So first of all, the quantum system encodes information in a fundamentally different way than the classical systems. So in the classical systems, the information component is called bit. So the state of the bit can be either 1 or 0, but in the quantum systems, we talk about quantum bit, in short, qubit, and it takes a coherent superposition state that takes aspect of 0 and 1 at the same time. So we usually describe the qubit in this so-called block sphere, and here the superposition state actually looks like this. And then this C0 and C1 called probability amplitude. And it's the square of the absolute of this probability amplitude gives you the probability of getting the state 0, 1. So the quantum computer actually strictly rely on these superposition states. And today I'm going to mainly focus on a so-called gate-based quantum computer. And this is kind of the analog of the classical computer. So in the gate-based quantum computer, we talk, so in the classical computer, we talk about the bit and gate, but in the quantum computer, we talk about qubit and quantum gate, like a single qubit gate or the multiple qubit gate. So how do these gates work? It's the following. So suppose that you have a 4 qubit systems, and then you have this superposition state, and then you want to get, let's say, your desired state in the output is 0, 0, 0, 1. So what you're going to do is you're going to design the gate, and then you design the gates such that the gate can manipulate this probability amplitude. And this probability amplitude behaves like a wave. So you can have constructive or destructive interference of the wave, the probability waves. And so you want to design this gate such that you manipulate this probability amplitude such that in the final output state, you want to get the probability of getting this 0, 0, 0, 1 is like nearly close to 1. So then you can get answer 0, 0, 0, 1. So like this is kind of very simple illustrations of the quantum computer. And because of this, it has been known that the quantum computer can outperform the classical computer in terms of the complexity. And because of this advantages, so people expect the quantum computer can solve many problems. For example, RSA key description, simulated chemistry, drug development, discovery new materials, or the early discovery of cancer cells, or root optimization, etc. So then the question is, the quantum computer was kind of like scientific curiosity, but now becomes growing reality. Then what was the factors behind this development? In my opinion, I think we can point out the 2 important factors behind this development. And while I'm a theoretical physicist, but I always curious about like the experiment. And in my opinion, I think the fabrication of good qubit systems and quantum control, developing the quantum control are the very important factors. So today in the laboratory, we can actually fabricate the very good quantum systems, qubit in the various platforms, and we can well characterize it. For example, the electron spins in the defects like nitrogen vacuum center in the diamond, or a superconducting circuit, qubit in the quantum dot in semiconductor platforms with atoms in optical lattices and photons. At the same time, people have developed quantum control protocols to efficiently decouple the system from the noise in order to keep the longer coherence time or the lifetime of the superposition state. And these are the kind of very important resources for quantum information processing. So today we can achieve this goal. And then the question is, what has been achieved from these technological developments? And so thanks for the development of hardware of fabrication and the quantum control. Actually today, quantum devices with the number of the qubits ranging from 50 to 100 is available. So this is called noisy intermediate scale quantum computer. In short, we call this a NISQ computer. And this is regarded as sort of a near-term quantum computer. So as for the properties, it is noisy, and it has a limited connectivity, and it has a limited number of the qubits. So because of this limited number of the qubits and connectivity, the quantum error correction is still a distant goal from the perspective of engineering, because if you want to do the quantum error corrections, we need thousands to millions of unset qubits, and we want to create very strong correlations between them. So it is still a very distant goal. So right now, very important ultimate questions about the NISQ computer is, can we do any quantum computing task by using currently existing NISQ device? This is kind of a very important questions that we asked today. So my research actually focusing on understanding the NISQ computers. So there's a chat, Q&A. Okay. So number one is the first question is, what are the requirements to achieve the reliable NISQ computers? And the second question is, what kind of applications can we do by using this computer? So for the first questions, I mathematically analyzed the trainability of the variational quantum algorithms. We have investigated the requirements for the trainable variational quantum algorithms, and then we investigated its physical insights of the trainability of the variational quantum algorithms. And for the second questions, I focused on the another branch of the quantum computer science called quantum sensing. So I developed the variational quantum algorithms for preparing the optimal quantum state for quantum sensing, particularly for the magnetometry. So let's take a look at one by one. So first, I'd like to talk about the reliability of the NISQ computers. So the NISQ computers have many envisioned applications, such as quantum chemistry, or solving the linear system, system of the linear equations, solving the combinatorial optimizations, and quantum, or solving the problems in the quantum networking, and the quantum sensing. So the idea of the NISQ algorithms is this is called the variational quantum algorithms. I don't know where to remove this. Let me remove. Not remove this. The variational quantum algorithms is regarded as the sort of leading strategies. So this is composed by a quantum classical optimization loop. So for example, suppose that we have a molecule and we want to find the ground state of the molecule. So in the initial state, we prepare one initial state, and we send this initial state of the molecule into the quantum computer. And this quantum computer, the gates of the quantum computer is parameterized by certain parameters, so say alpha. For example, this alpha can be the amplitude of your microwaves that you apply to the nucleus spins in the molecule. Then you're going to measure the energy of this molecule. Then you can get the average energy, which becomes a cost function. And this cost function is the function of the parameters you want to tune. And then we send these cost functions into the classical computer. And then we use the gradient descent optimization method to find the minimum, the optimal parameters, such that the parameters can minimize this cost function. And then we do this loop over and over again, and until in our output state, we can get the ground state of the molecule. Like, so this is actually the ideas of the variational quantum algorithm. So focusing on the variational quantum algorithms, we can say the reliability of the NISQ computer can be interpreted as the trainability of the variational quantum algorithms. So then the question is, what are the conditions of achieving the trainable variational quantum algorithms? And in order to answer these questions, we have to first know what is the metric that measures the trainability of the variational quantum algorithms. The metric actually is given by the variance of the gradient of the cost functions over all the parameters that you want to tune. So then the question is, where does it come from? Why we need the variance of the gradient of the cost function? This is actually coming from Shifts inequality. So what does this inequality really mean? So if we translate it to English, then this means the probability of non-zero gradient is suppressed by its variance. Okay, so and then if we were going to illustrate it by using simple example, so we can think the problem in the following way. So suppose that we want to train two parameters, alpha 1, alpha 2, And then we want to find, we want to find the minimum of the cost function. So if the variance of the gradient of cost function is very small, like in the exponentially small, then the graph is like, it looks like this. The landscape is really flat. So this means it is likely for us to start from the outside of this gorge. So if we start from the outside of this gorge, actually we would take more steps to get to the minimum of the cost function. But so it's really hard to train. But if the variance of the gradient of the cost function is large enough, so for example, if it is in the order of 1 over poly n, where n is number of qubits, then this means it is more likely for us to start from the inside of the gorge. So it's inclined like this. So in other words, so we would take much less steps to get to the minimum. So it is getting easier to train. So this is the connections between the trainability and this is connections between the trainability and the distribution inequality. And from this, we say, yes, so we can use the variance of the gradient of cost functions as a metric to measure the trainability of the variational quantum algorithm. So, and then we working on our general structures of the variational quantum algorithms and analyze its trainability. So we consider two cases. For one case, we consider the cost function. Here, n is the number of qubits, and for the x-axis is the circuit depth. Basically, circuit depth is defined as the number of the layers that are constructed by the gate in parallel. So with this structure, if we measured all the qubits at the same time, we call this a global measurement. If we measure the qubit at the same time, regardless how deep the circuit is, as you increase number of qubits, you will have exponentially larger number of the steps to get to your solution. So in this case, we have proved that the variation, the variance of the gradient of cost functions is in the order of 1 over 2 to the n, where n is number of qubits. But if we measure the qubit one by one in the sequence, we call this a local cost function. Then what's going to happen is, if you have a shallow depths, like in the order of log n, then you can actually achieve the trainability. So the variance of the cost function gradients is in the order of 1 over poly n. However, of course, if you increase number of layers, then you can achieve, you can hit the untrainable regions. But if you have the local measurement and shallow depth, circuit depths, then yes, you can achieve the trainability. And we also did this with the computer, with the simulations. So as you can, so the red line here is the global cost function, and the blue line here is the local cost function. As you can see, if you have a smaller number of qubits, yes, the global cost function still works. So because you want to, you want to see the cost functions going down, because you want to find the minimum of it. But if you increase number of qubits, as you can see, the global cost function becomes flatter and flatter and flatter. So, but still, so flatter and flatter, so it's hard to train. But the local cost functions keep going down, regardless how many qubits increase. So it's still trainable, even you have like larger number of qubits. Actually, we did simulations until like 100 qubits, and still we can see this phenomenon. So, and then we can say, yeah, so condition of the trainable variation quantum algorithms, we need two conditions. One is local measurements, like we want to measure the qubit, like every single qubit one by one, and we need a shallow circuit depths. So we can also see this phenomenon with a very simple example, like the one layer variation quantum algorithms with Tensor-Product form. So suppose that we have like input state, like all zeros, and we want to send this input state into a Tensor-Product gate. where X is just a Pauli matrices, X Pauli matrices. So you want to rotate the state by X with by some angles alpha 1 to the alpha n, and then you can get alpha state. Suppose that our goal is to get its original state, like 0, 0, 0 state. So yes, so we know, okay, alpha 1 to alpha n can be 0. But let's say we want to train these parameters and want to find the optimal parameters. So this is just a simple example. And then the global measurement is defined as the following. So basically here 0, 0 means it's a projection measurement that gives you the probability of all the output states are 0. And then we compute the global cost function, and the global cost function becomes this way, becomes this. And then if we compute the gradient, the variance of the gradient, we can find that this is given by 1/3 times 2/3 or 3/8 to the n. So this part is exponentially decreasing. As you can see, the variant, this means that this means that if you increase the number of qubits, then you will need more and more and more steps to get the desired alphas. But if we do the local measurements, where the local measurements is defined in this way, so this is still the projection measurement that gives you the probability that kth qubit is in the state of 0. So if we do this local measurement, then we can get this local cost function. And if we compute the variance of the gradient, as you can see, this is given by 1/8 times n squared, which is polynomially decreasing. So this means that at a very reasonable time, we can find the optimal parameters of alpha 1 to alpha n. So by far, this is the mathematical analysis. Then, but as a physicist, we want to ask the question, say, hey, what is the physical intuition behind this trainability of the variational quantum algorithms? And then, in order to answer this question, we considered a very specific model of the variational quantum algorithms, which is called Hamiltonian-based VQAs. We focused on called quantum approximate optimization algorithm. In short, it's QAOA. So QAOA is, as you can see, is composed by each layer is composed, each gate, each layer is dependent on a particular Hamiltonian, HP or HB. And these alpha and betas are the parameters that we want to tune. So the HP is called problem Hamiltonian. In the QAOA, this is usually, we usually regard it as sort of a classical IC model Hamiltonian. And HB is called a mixing Hamiltonian. Basically, it corresponds to applying some transverse field to your spin system. The goal of this algorithm is to find the ground state, like ground state of the HP. So, and as for the properties, this has the form of quantum control model with a band form. So basically here, we call this a band form because we apply control here, band, and we do this like, we call this the band form quantum control. And this actually is used for solving some combinatorial optimization problem. So for the results, if you think about spins, many body systems, then if the coupling strings between the coupling strings between individual spins follow some binomial distributions, then we have found is the mean or the variance would determine the trainability of this QAOA circuit. But still, also this mean and the variance would determine the controllability of this system. What we have found is there's a trade-off between the controllability and the trainability. So, and we figure out this is actually the physical intuitions behind the trainability. So I'm going to explain, I'm going to show the physical intuition behind this. So let's ask questions. What does it really mean by more controllable? Here, the more controllable it is harder to train. So what does it really mean? So if you think about the definition of the controllability, when the system is more controllable, this means if you have an initial state and desired final state, then you have more paths that you can access to get the desired state from your initial state. So because this is controllable, but if you have more paths, then it is getting harder to train because you have to find the optimal path from many accessible paths. So it's harder to train. But if your system is less controllable, this means it will become easier to train, because if it is less controllable, this means you have a smaller number of accessible paths from your initial state to desired state. So from the perspective of trainability, you just have to train a smaller number of the paths. So it's getting easier to train. So this is kind of like one of the physical intuitions behind the trainability of the variational quantum algorithms. But this explanation can only hold for this Hamiltonian-based variational quantum algorithms. If we talk about like a more general form, I think this is still the open questions. But at least if you think about Hamiltonian-based variational quantum algorithms, we can see a very clear intuitions, very clear interpretations to the trainability of the variational quantum algorithms. So then now we have learned the constraints of achieving the trainable variational quantum algorithms. The next question is, what can we do by using this NISQ computer, by using variational quantum algorithms? In order to answer this question, I focused on another branch of the quantum information processing called quantum sensing. So quantum sensing is a very promising and very exciting field because it has multiple interdisciplinary applications to the various fields. For example, we want to use the quantum sensor to achieve the precision measurement beyond the classical limit. For example, we want to identify the molecular structures. We want to study the magnetism of the 2D materials. We want to use quantum sensor to study the living systems, measure the temperatures of the cells. Also, we want to use the quantum sensor to do, for example, the gravitational wave detection by using squeezed light state. Or we want to use the quantum sensor to right now there's a challenge to use the quantum sensor to detect the dark matter from the distribution by sampling the distribution for the damage due to the nuclear collision. So as you can see, the quantum sensing is a very exciting field right now, and so it is meaningful to ask the question, say, hey, can we combine can we use the quantum computer to help the quantum sensing? So a very important quantity in the quantum sensing is called quantum Fisher information. So in order to talk about quantum Fisher information, let's see a very simple illustrations of quantum sensing. For example, let's talk about the magnetometry. So suppose that here we have a magnet, very small magnet, maybe it could be a proton or something. And then what we want to do is, so here the magnet produces some magnetic field. Let's say this field is theta that we want to estimate. What we're going to do is we prepare a quantum system and we prepare a quantum state, let's say raw, and the quantum system here is dealt with as kind of a probe. So what we want to do is we want to have this system interacting with this magnetic field theta. So let's use this W theta as operators describing the interactions between the magnetic field and the quantum system. Then the system will acquire some phase. The phase is parameterized by this magnetic field theta. So the system will be parameterized. So the state will be parameterized. So let's say this state is rho theta. So what we want to do is we want to take the measurement, and from the measurement result, we want to estimate this theta. So of course, this estimation has some error. So the variance of this unbiased estimator is overbounded by 1 over I theta rho. And this I theta rho is called quantum Fisher summation. So intuitively, the larger the quantum Fisher summation is, the precise your measurement, the precise your measurement could be, because you can get more information about the system. Sorry, about the parameter theta. So this quantum Fisher summation is dependent on your probe state, the state that you initially prepared for doing the sensing. So from this equation, we can say the quantum Fisher summation measures the sensing performance of the quantum system as a sensor. As you can see, the larger the QFI is, in short, the quantum Fisher summation is called QFI. So the larger the QFI is, the better the quantum sensor, the better your state initially prepared is. So this is kind of, so you can use the QFI as this measure. However, quantum Fisher summation is very hard to compute based on quantum computer. Particularly when the system is in the mixed state. So it is very hard to prepare the pure state in reality because there's always a noise. So the state is always mixed state. And then if you have a mixed state, then the quantum Fisher summation is nonlinear to the principal components of the mixed state. For example, it's eigenvalues with eigenvectors. So then the question is, what we need is the metric which is computable with quantum computer to prepare the optimal state to maximize this quantum Fisher summation. So like, this is the question that we are asking. And then we have considered many proxies of the quantum Fisher summation that are computable based on quantum computer. Then one of them is called sub-QFI. So this is the proxies of quantum Fisher summation that is computable by using quantum computer. So it has a very, very important properties. One is sub-QFI is the lower bound of QFI, but it has a very important property. It shares the same optimal probe state, rho star. So what does it mean? So the rho star, rho star is the state that maximizes the sub-QFI. At the same time, it maximizes QFI. So then this means if we use sub-QFI, that would be great because we use the quantum computer to compute sub-QFI because sub-QFI is computable as a quantum computer. And then we do variational quantum algorithm and we prepare the optimal probe state, rho star. Then this rho star can directly maximize the QFI. So we don't have to compute the QFI directly. We just have to compute sub-QFI to achieve maximizing the QFI. So this is the idea. So this is the take-home message. Sub-QFI and QFI share the same optimal probe state. Then the question is, what is so how does this quantum circuit look like? This look like this. So basically, we need a unset qubit, and we prepare 4 copies of a quantum state, let's say rho, and we send this rho into a parametric circuit. So this red part actually corresponds to optimal probe state preparation. And then we send system 1. We have the magnetic field interact with this system. For the system 2 and system 4, we have system 2 and system 4 will interact with magnetic field with some error, epsilon. Then we do there's a swap test here, and then we measure 0, state and 1, state of the unset qubits. So the measurement on this unset qubit will give you the sub-QFI. And then we send the sub-QFI to the classic computer and optimize the parameters. And we optimize its alphas such that the output state here, after this red box, is the optimal state for the sensing. So here the point is sub-QFI is, so from this we can see that sub-QFI is computable based on quantum computer, and optimal state can be prepared through the variational quantum algorithms on the NISQ computer. So in the conclusion, this is a take-home message. Basically, the NISQ computers are reliable, but under a certain constraints of the local measurements and shallow circuit depths. So still, the variational quantum algorithms, I would say, is not like very powerful, but it has a constraints. But within these constraints, we can use the variational quantum algorithms to prepare the optimal state to achieve the precision sensing, particularly for the quantum magnetometry. So for the exciting path forward, we can extend the single parameter estimations into multiple parameter estimations. For example, we can think about quantum networks. We can have the networks of the spins and have each spins interacting with the different magnetic fields. And the question is, can we design a quantum variational quantum algorithms to prepare optimal states such that the states can give us the most precise estimations of these parameters or some statistical values of these parameters. For example, the weighted average of these parameters. So, and now this problem become more and more complicated. So we need a new metric as the cost function that is computable as a quantum computer. And the other question is, can we develop the variational quantum algorithm for optimal probe state preparations for this multiple parameter estimation? And the other very important question is, now we talk about state preparation, but we also need optimal measurement to achieve this precision. So the question is, can we also develop the VQAs for finding optimal measurements or not? And then again, then this computer is no easy. So by far, we considered only the case that we ignore the effect of noise. But the next question is, what if we have a noise? If we have a noise, we have to do noise mitigation. So the noise mitigation is very important. And then we want to propose how to implement these algorithms on different quantum platforms. So these research actually can deepen our understanding about variational quantum algorithms for sensing, but also because we want to think about like noise mitigation stuff. So this can help us to deepen our understanding about open quantum systems and also entanglement, quantum networking. And we also can ask the questions about quantum advantage in NISQ computers. And because we deal with the quantum network, so we want to consider this research can help us to study the quantum simulations and condensed matter physics, and also can help us to develop our understanding about quantum multiple parameter estimation. So for the acknowledgement, I'd like to thank to my PhD supervisor, Professor Paolo Capellaro from MIT, and to thank to Dr. Patrick Holtz, Dr. Marco Cerezo, and Dr. Lukasz Cinsil, and Dr. Tyler Mofko from the Quantum Computing Group, Los Alamos Central Laboratory. I'd also like to thank to Professor Pranita Narang from, right now she's in the UCLA, but she was in the Harvard. And also like thank to Professor Chinta Zhuang from University of Southern California. And I'd like to thank to Jacob Becky, who is a PhD student right now in the University of Colorado Boulder, who did many excellent works in the simulations of the quantum variational quantum algorithms for the quantum sensing. Still, the quantum sensing and the quantum variational quantum algorithm still have a lot of open questions to explore. So we'd like to collaborate with each other and explore this exciting journey together. So thank you very much for your attention.
Questions and Q&A, so we'll start there. Moving on to the questions, chat and Q&A.
No, can I open this? I cannot open this actually. Should I do this? We can't see. Oh. Is the desired state also the final state? Is this desired state also the final state? Yes, the desired state is the final state. Yes. I think the desired state means this one. Oops, sorry. Yes, so the desired state is the final state that we want to get right here. So basically, desired state. Hopefully, the desired state is the ground state of the problem Hamiltonian. And is there any questions? Yes, perfect. It's Jing. Oh, so Jing asked questions about like whether whether the quantum sensing is only about like magnetic fields or it could be applied to the different physical quantities. Well, actually, yes. So quantum sensing. So now I'm talking about like quantum magnetometry, just for an example. But we can also have quantum thermometry, which measures the temperature of the cells. And also we can use the quantum sensor to do electric field. Since the electric field, for example, the neurons, the electric field produced by the neurons, magnetic field produced by neurons. And now the people are also interested about like whether we can use the quantum sensor to detect let's say the gravitational waves or some dark matters actually. So the dark matter, they say it hit some like crystals and they have like a distribution of the damage, and then basically the phonon. And then you want to use for example, nitrogen vacuum center to detect this sample this distribution. So those are kind of everything is about quantum sensing. Yeah. Yeah, please. Yeah. Yeah.
It looks like you actually use conventional filter for optimization. Is it like actually this will always need to use that?
So Jing asked two questions. One is whether the IBM's or the Google's computer can be considered to be a NISQ computer. And the second question is, do we always need the classical counterpart device to do the optimizations for the quantum computer? Actually, for the first questions, I would say yes. So right now, I would say the quantum computer in the IBM and IBM in the Google are the NISQ computer, because still the quantum error correction it hasn't been done yet. So yes, it is a NISQ computer. So in other words, this is currently this quantum computer. And for the second question, do we always need the classical counterpart? So in the future, we want to replace the classical counterpart with quantum computer, to like have this fully quantum computer stuff to do everything. But now still we need the classical computer to do this, because the idea here is like, so the cost function, we want to use the quantum computer to compute something very hard to compute by using quantum computer as a cost function. So, and then once we did that, so right now the gradient descent optimization can be done by using classical computer, but it's, I think still have to we haven't figured out how to do that, so all of these things in the quantum computer. So we want to sort of use the classical computer to assist the quantum computer to complete this task. So the cost functions usually is hard to compute by using classical computer. So for example, this is SubQFI. If you using classical computer to do this is sort of like, it will take a long time, I would say. But if you use a quantum computer, you have to just use the quantum circuit, efficiently compute the cost function. But then the question is, how can we do like optimization? Then you haven't figured out how to use a quantum computer to do that. So why not using classical computer to assist this task? So this is the idea behind this. Yeah. Maybe, yes. Okay. So thank you very much for attention.
Thank you.
You're welcome.
Thank you.
So should I leave or? Oh.